MZmine is a popular Java-based open-source mass spec workflow software that will run on Windows, Mac, or Linux with a valid Java virtual machine and the open-source R statistical package installed. Veritomics has adapted the standard MZmine version 2.19 to incorporate our public Peak Investigator Application Programming Interface, or API. We will refer to this as the MZmine Peak Investigator Edition, or MZmine PI, in this tutorial. The relevant source code is available from Veritomics. This video explains how to use the added Peak Investigator components in a basic LCMS analysis. We assume that you have already downloaded and installed MZmine PI from the Veritomics website. As illustrated here, when you open a project in MZmine and access Peak Investigator, the raw LCMS profile data is compressed and sent to the Veritomics servers. The servers process this data usually within 24 hours, and the resulting spectral mass lists can be downloaded directly into the MZmine project for further processing, just like any other centroided mass list from within MZmine. This is the main MZmine screen. The raw data will appear on the left and the chromatographic data will be on the right. Progress bars for all tasks will appear in the bottom panel. The first thing you will need to do is add your Veritomics user information to the MZmine preference panel. In addition to the standard MZmine preference settings, you will need to add your Veritomics user information. Enter your registered Veritomics username, password, and account number that you were given upon registration with Veritomics. These data are saved in the MZmine preferences file so that you need only enter them once. In addition to these data, you will need to point MZmine to the nearest Veritomics server. This defaults to the US server. When complete, hit OK and this information will be saved. Now you will need to import a project. MZmine supports many OpenMS formats like MZML, MZXML, and MZData. Here I am importing some MZML profile data from a plasma lipidomics run, and the same run centroided using the vendor's software in MZData format. These formats are automatically converted by MZmine into its internal data format. Clicking the triangle opens the dataset to display the individual scans, which are indexed by both chromatographic retention time and scan numbers. Here we select a centroided scan to display it. The scan display lets you zoom in on specific features. Here we select a profile scan to display. Unfortunately, MZmine does not recognize the vendor's centroided scan files as centroids, so we need to use the mass detection / centroid option to create a centroided mass list for MZmine to process. We are only interested in a small retention time region for this demo. Since these data have already been baselined and thresholded, we can leave this option set to 0. Now we can open a scan and see that the standard centroiding mass lists that were generated lie directly on top of the original vendor centroids. Now we focus our attention on the profile data, which we are going to process using Peak Investigator. First, we select the profile dataset. Again, we select the mass detection menu option to get the pop-up window. First, we select the mass range to process. Again, we are only looking at a narrow retention time range for this file. the same range we processed previously for the centroided. Then we select the Peak Investigator centroiding option. Since baselining and thresholding are automated within PI, the only user option is to narrow the mass range to be centroided. In this case, we are processing the full mass range of the spectrum. You can preview the spectrum to get a visual of the mass range and even move forward or backward through the scans with the arrow keys. Under the PI Options panel, you may narrow the mass range process to help control processing costs. You may also choose the version of MZmine PI to use for this analysis. Veritomics is committed to supporting back versions of its software and remembers the last version that you used. This allows users in regulated environments to complete long studies with a single validated version and upgrade to newer versions and features as their work permits. Next, we select a unique name for the spectral mass lists. In this case, PI. When we hit OK, metadata about the size of the job is collected and transmitted to the Veritomics servers to provide a cost estimate for the job. Veritomics analyzes the metadata associated with your job to provide a cost estimate for the job as you've specified, based on the number of scans, file size, and mass to charge range for each supported mass analyzer type. The type of mass analyzer is determined automatically by PI after the job is submitted. If you have insufficient funds in your prepaid account at Veritomics, you will receive that message here and will not be able to submit a job until more money is added to your account. Veritomics supports different levels of service. Those available to you in your account will be displayed for you to choose from. The faster the response time requested, the more computer hardware we must allocate to process the job, and the more money we must charge. When you hit Purchase here, you are committing to processing the job. Your account will be debited the estimated cost once the spectral data has been successfully transmitted to Veritomics. If the actual processing costs are less than this estimate, your account will be credited the difference once the job is completed. Your account will never be billed more than the estimated cost. We hit OK and the job starts uploading to the Veritomics servers. Note, while the files are being uploaded, you still have an opportunity to cancel the job. No job will be started until all the data is received by the server. However, once the transmission is complete, the job will be processed and your account debited accordingly. Now you should note, when the transmission ends successfully, a unique job number in the cloud icon here is placed into the data directory. This is a unique feature in the MZmine PI edition. We use this unique job identifier to anonymize your data on the Veritomics servers. If you lose this information, your results cannot be retrieved. You will click this cloud icon to retrieve your spectral mass list back into this MZmine project. It can take Peak Investigator 24 hours to process a job. We automatically scale a sufficient number of cores into our grid to complete the job within the targeted timescale. If PI hasn't completed processing your data, you will get a status message. The job is first pre-processed to ensure spectral data consistency, then the job is run. The appropriate job status message is displayed each time the server is queried. You can submit additional jobs as part of the same project or from a different sample in a multi-sample project simultaneously. A unique job identifier will automatically be created for each job submitted and stored in the job folder. However, we recommend that you save your MZmine project immediately after job submission to preserve these cloud icons. Once the project is saved, you can safely exit MZmine. The Peak Investigator API uses standard gzip and SFTP protocols to compress and encrypt your data for transfer to the Veritomics servers. Any identifying metadata is stripped from the headers and checksums are added to each scan to ensure that the data is not corrupted during transfer. A unique job number is assigned to anonymize your data. The cloud icon within the data directory from which the scans originate is labeled with this unique job number. The job cannot be retrieved without that identifier. Once you hit purchase, the job is committed and you will ultimately be charged the lesser of the actual or estimated costs upon job completion. When Peak Investigator processes your job, it will automatically determine your mass analyzer type and check the data files for self-consistency. If you try to mix scans from different projects or covering different mass ranges together, it will reject the job. PI uses proprietary baselining and thresholding algorithms that are fully automatic and locally adaptive within each scan, so you always get the same result and don't have to guess at what will work best. PI uses advanced signal processing algorithms that auto-tune to your submitted data. With these auto-tuned signal processing algorithms, Peak Investigator simultaneously centroids and deconvolves the peaks in each spectra. These algorithms more than triple the native hardware resolution of any mass analyzer. The best part about PI is its statistical validity. You get less noise and more signal more reproducibly. Now that some time has elapsed, we can reopen the saved MZmine project to check on our job. Each of the original data sets in the project open, and we can go into the profile data to find the icon for our job. This time, when we right-click on the cloud icon, the job is complete and the download of the PI spectral mass lists begin. When this completes successfully, the cloud icon disappears and the files are deleted on the Veritomics server. So save your work, as this is now your only copy. If the download is interrupted for any reason, the cloud icon will remain and you can try again until the download is successful. Here we see that the mass lists are sorted into the dataset by appropriate scan number as they are retrieved from the Veritomics server. If we click to open one of these, we see the PI centroids are now displayed. Now that we have the spectral mass lists, we can use the standard MZmine features to build the LCMS chromatograms. This process compares the mass lists from each spectrum, aligning those centroids within a specified mass tolerance into a chromatogram in the time domain at that mass. We limit our chromatograms to the retention time region of interest in this study. Since you can perform more than one type of centroiding on a dataset, you must specify the name of the mass list to be used. In this case, it's the vendor centroided set. We have to select the minimum time span that defines a chromatographic peak, in this case 0.045 minutes, which corresponds to between 5 and 6 consecutive scans. We also specified the minimum acceptable height for a peak, which we have set to 0 here because we have already thresholded during the centroiding process. Most importantly, the mass tolerance used to distinguish one peak from another must be specified. This mass tolerance parameter can be specified in absolute mass or ppm. This parameter must account for any calibration drift during the run, as well as the inherent instrument resolution and centroiding precision. The mass tolerance setting must be guided by user judgment, often by analysis of the variation seen in the calibration samples run before and after an LCMS run. This process is repeated for the Peak Investigator dataset. When the chromatograms are completed, a new dataset is created in the chromatographic peak data window to the right. If we open this, we see the individual chromatograms created for each mass that meet our selection criteria. The retention time, apex, and chromatographic peak height and area are automatically calculated. A separate chromatogram is created for each unique centroid in the corresponding mass lists that replicates through enough consecutive scans. Here we display a chromatographic peak as a function of retention time found at a mass near 809 Daltons. Now that the chromatographic peak lists are complete for both datasets, we can proceed. As you saw in the previous chromatogram, there can be a long tail. There can also be multiple chromatographic peaks that appear at different retention times in the same chromatogram. For example, cis and trans isomers of the same olefinic species that elute at different times. These must be deconvolved to create an accurate chromatographic peak list. This is done with the chromatogram peak deconvolution feature. We select all the peak lists, assign a suffix name for the deconvolved peak lists. There are several methods available to accomplish this task. In this case, we know the two files should be identical, so we use the simplest option. Now that chromatograms have been constructed from both datasets, we can align them to see if there are any differences. In this case, both data sets started from the same profile data. One was centroided by the vendor's software, the other by Peak Investigator. Since we are now working from the chromatographic peak lists, we go to the peak list menu and select the join aligner. This will combine the peak list information from both the deconvolved chromatographic peak lists that we just prepared. Here we select the deconvolved peak list to use in the alignment and give the aligned master a name. Then we specify the mass tolerance and retention time tolerance for this alignment. In this case, we know the two peak lists should overlay nearly exactly since they are derived from the same original data set. Therefore, we can set tight mass tolerance limits. Again, these parameters must be set based on your best judgment using your knowledge of how much run-to-run variability is typically seen in your instrument setup. When we hit OK, an aligned peak list appears. If we open this, we see a master list to the left of all the unique peaks found between the two samples, and to the right, the actual chromatographic peaks that appear in either one or both samples. We note here that there are several peaks that appear in the PI centroided data that have no corresponding entry in the vendor centroided peak list. One such new peak is at 809 Daltons. Here we see two peaks at the same retention time and another nearly isobaric peak that hits its apex at a slightly different retention time in the Peak Investigator centroided sample. If we go to examine these peaks in the original spectrum at the first retention time, we see that indeed Peak Investigator finds three distinct peaks in this spectrum, shown in blue. But standard centroiding finds only one, in red. The original sample was rerun in a higher resolution instrument shown reflected below the lower resolution spectrum, and we can confirm that there were indeed three peaks at this mass position of the approximate abundances found by Peak Investigator. A similar example is shown here, where a nearly isobaric peak was completely missed by standard centroiding, but its presence and abundance were clearly influencing the mass of the centroid. The top graph shows a time slice of the chromatograms for these peaks. The backmost chromatogram in black, the two peaks were unresolved by standard vendor centroiding, even though there was a noticeable mass shift in the position of the standard centroid in the lower graph. Peak Investigator found both nearly isobaric peaks and correctly deconvolved these with both mass and abundance consistency. That completes our tutorial of the MZmine Peak Investigator Edition software. MZmine PI can be downloaded from the Veritomics.com website, where you can also sign up for a free demonstration account. Thank you.